Hi, we've seen that we have these objects that have either upstairs or downstairs indices. Again, we have these contravariant vectors and covariant vectors, or we can have more generally tensors with some combination of upstairs and downstairs indices. And we've seen that the same object with an upstairs versus a downstairs index, they're related in special relativity up to just some minus signs. But we haven't learned how, if we know, for instance, the value of some object, some tensor with upstairs indices, how do we get to the object with the downstairs indices? So how can we really quantify this relationship between these objects with these two different types of indices? Well, we raise or lower indices using an object known as the metric. This is a rank 2 tensor that's used to raise and lower indices. In special relativity, this object is going to be fairly simple. If you go on to do general relativity in the future, then this object ends up being a more complicated object, and it's going to define your or relate to the curvature of your space-time that you're in. In special relativity, we're always assuming we're in the limit where space-time is perfectly flat, and so this object is quite simple. But keep in mind, if you go on, it could get more complicated if you do general relativity. So in special relativity, our metric is referred to as the Minkowski metric. So this is the metric for flat spacetime. And this is the one that we use in special relativity. That's our special relativity. G mu nu is often the letter that's used for the metric in general. Sometimes people use eta mu nu when they want to specifically talk about the Minkowski metric. So this G can sort of be used for any metric. Whereas eta, when you see eta, usually someone's specifically talking about the Minkowski metric. If you're doing special relativity, people sort of use G or eta interchangeably because we just have this one Minkowski metric that you deal with in special relativity. But I just wanted to mention that in case you look at different references and you're wondering, what's this G versus this eta? Well, when someone says eta, they specifically mean the Minkowski metric for sure. When someone says G, they might mean more generally a different metric. But if you know you're doing special relativity, then that G is going to be your Minkowski metric. So in this class, these two names are interchangeable. And we can write this out, and it's going to look sort of like, almost like the identity, except we're going to have those fun minus signs. Where we see this is symmetric, and we see that it is all of the minus signs are associated with sort of our spatial terms. I'll mention that if you look at a general relativity reference, so this is the convention that's used in particle physics. If you read general relativity, often they'll associate that minus sign with the time component, and then the three spatial components are positive. And again, this is just a different of conventions, and the thing you just want to be careful about is that you don't accidentally use both conventions at the same time, because then you're going to mess up your minus signs. So just make sure that you stick to one convention, and this is the convention that's usually used in particle physics. Okay, so this is an object which we are going to use to raise and lower our Lorentz indices. So let's first talk about lowering. And we'll do specifically the example of a 4 vector, just to keep it simple for now. We already know when we introduced 4 vectors, we said, okay, you have this object that has an upstairs index, and maybe we know its components, and the downstairs one, we just tag on some minus signs. Well, now we can see where these minus signs are coming from, and they're going to come from multiplying by this metric. So for instance, if we are given some vector a mu, this is a 4 vector, again, and maybe it's a0, a1, a2, and a3 has 4 components, then a nu is going to be equal to g mu nu a nu. Oh, excuse me, I just messed up this is not an allowed equation. So a mu, I suppose. So that we have our mu's, which are said to be contracted, they're our repeated index, and we're left with a nu on the bottom. So, right, so these guys are summed over. We'll learn soon that they're referred to as bound indices, these ones that are summed over, that's another term. And then we're left, so that sort of goes away, and we're left with the nu on the bottom. And I don't really want to go through all the details of this, but just to make sure you really understand this concretely, let's consider the case where our new index is our x component. So what does this equation say for that case? So here I'm looking at, or I guess I should call it 1 instead of x. Again, because maybe I'm not working in Cartesian coordinates. So what happens what is A1, our first spatial component with the lowered indices? Well, this is going to be equal to g, and nu is set equal to 1. I'm writing an equation where nu is set equal to 1, but mu is being summed over. So we have 0, 1, a 0. And then we have another term, g1, 1, a1, plus another term, g2, 1, a2, plus another term, g3, 1, a3. But this is a diagonal matrix, right? Only our terms that have our 2 indices like g11 or g22, only those terms on the diagonal are non-zero. So all these off-diagonal terms are 0. So this becomes g11a1, and g11 is minus 1, right? So this is minus a1. So here we're seeing we get that key minus sign that we want when we're dealing with now the downstairs version of our vector. And I encourage you to do this same calculation for our time component, and then at least do it for 2 just to really see. And if you really want to bring it home, for 3. And we expect for our A0 component, that's our time one, there shouldn't be a minus sign. Right, so we expect a nu with downstairs to be A0 minus A1 minus A2 minus A3. So go through it for those other 3 components to make sure you really understand what's going on here. Now, I wrote this out as a matrix, and so you might be wondering why I'm not doing matrix multiplication here. Well, actually, we can. And I encourage you to try to do the matrix multiplication here to see that we also get the same answer. I don't like doing that always because it's easy to get a little confused about which one is the row and which one is the column, and how are we multiplying these things together if we write them out as matrices? So I find that students, when they're first learning this, sometimes get a little confused about that. Whereas doing it the way I just did below, you're not going to get it wrong. So but I encourage you to also to play with that to make sure you understand how you would do it with a matrix. So this is the example of how we can lower the index of a 4 vector. We can lower the index of tensors more generally. And we do it in the same way. So if we have some tensor new row, we want to lower one of these indices, we can multiply it by g mu new, where notice I have this repeated index again, and then what you're left with is t mu. So the news are repeated, so they're going to go away, and we're left with a mu, and then our row is still up top. That index isn't affected. Or if I have t new, and then maybe the row was downstairs to start. Now this is t mu row. All right, so we can use this to also, or maybe just for one more example, we could use it if we have new row sigma, rank 3 tensor, then hopefully this does exactly what you would expect, right? The other guys just come along for the ride. Okay, so that's how we lower indices, but we might, what if you're given an object with a lowered index and you want to raise it? We're going to do this with the inverse metric. So the inverse metric is g mu nu upstairs, or again, if I want to stress that I'm using the Minkowski metric, we can write it as eta. But again, in this class, we're doing special relativity. So this is, when we say the metric, we always mean the Minkowski metric. Happily, for special relativity, the sort of values of our metric are going to be the same. So this g mu nu looks exactly the same as the object with lowered indices. Remember, in general, an object with upper versus down lower indices is different. But in this case, happily, it's the same. It's the same. Yay. Again, in general, objects with upper and lower indices, their components are going to look different. In the case of special relativity, our inverse metric looks the same. And so that makes things kind of easy because you just have one thing to remember. And we can use this now to raise indices. So g mu nu multiplied by some vector with a downstairs index. This now becomes the object, the vector with the upstairs index. G mu nu, maybe on a tensor. Oh, excuse me, but we need to contract again one of them. This becomes T mu upstairs, sigma, and etc. for higher ranked tensors. So, and it is important, right, that we have this contraction, we have this repeated index when we are raising and lowering our indices. And I encourage you, especially in this case, this simple case of a 4 vector, to do what I did previously up here and check that your minus signs work out in the way that you would expect. All right, so that's the basics of how you use the metric to raise and lower indices. Thanks for listening.